Welcome to week 5, and this week we're going to be looking at specifically a class of differential equations we have not covered yet, and that's the non-homogeneous class. We're also going to look at some applications of that in practice. So far, what have we looked at? Well, we've looked at differential equations, which were nth order, and were linear, and had constant coefficients. However, we always insisted that this right-hand side would equal 0, which was the definition of a homogeneous differential equation. This right-hand side was essentially missing or didn't play a role in the calculation. Now it turns out that a lot of interesting applications don't have zeros on the right-hand side, and so our natural next step is to explore that possibility. So how does having some function of x, and the key thing here is that there's just no y's, but we can have potentially any function of x here on the right-hand side. How does that play a role in our solving? Well, this little theorem or lemma here is going to help us out. If we have two solutions to the non-homogeneous, so in other words, if I plug y1 into this, I get f of x. If I plug y2 into this side, I get f of x. Then what can I say about the difference between them? Well, let's take a look at that. What we're going to do is plug both of these into the left-hand side. And what do we get? Well, if we're going to plug in, let's call this whole thing here y. It's a linear combination of those two. If we take two derivatives of it, we just take both derivatives separately. And then we'd have p of x times the derivative of this y, which is the derivative of each one of these individually. And last but not least, we'd have q of x times y1 minus y2. And then we just simplify. We can group these. We'd have y1 double prime plus p of x, y1 prime plus q of x, y1. That makes a nice grouping. And then we have minus. Well, if you have the minus at front of this, we had a little minus that should be there. All of these terms have a negative y2, negative y2, negative y2. Let's bring the negative out front for all of those. And we'd have y2 double prime plus, because we have the negative out front already, p of x y2 prime plus q of x y2. And that, well, that looks an awful lot like the original left-hand side of the differential equation. And that equals f of x because y1 is a solution to the non-homogeneous differential equation. Well, wait a minute. The same logic applies here, except it's because y2 is a solution, etc., etc., etc. So this is also equal to f of x. So what we have is f of x minus f of x, and that sounds like 0. Aha! So what is that telling us? That the difference, if I pick any two solutions to this original equation, and I compare them, I take one minus the other, I'm going to get a solution to the homogeneous version. Okay, the implications might not be totally obvious there, so let's explore that a bit further. It's going to be tremendously helpful though. A conclusion from that proposition is that if we look for the general solution of the non-homogeneous differential equation, it will be made up of a bunch of constants times y's, unknown functions yet, plus one new thing. And this yc part here should look awfully familiar. It's called the complementary solution, C, and sometimes it's called the corresponding homogeneous equation. So C for complementary or corresponding solution. And the idea is we get this by solving the differential equation with no right-hand side, and then we add in this little extra term. It's a specific solution that applies to the non-homogeneous part. And that's it. So we can really leverage our solution from before, the homogeneous one, and we're just going to tack on one little thing at the end, maybe a big thing at the end, but still one single function for handling the non-homogeneous part. And you can see with this form how that proposition would lead us here, because if we had y1, let's call it ya, and minus some other solution yb, We might have different solutions to the homogeneous part, but this part would be the same. So we'd have some stuff plus y nh here, non-homogeneous solution, minus some other stuff plus the y non-homogeneous. These would cancel, and we'd end up with the difference of solutions, or a linear combination of solutions to the corresponding part. Now this, quite frankly, I think makes more sense when we look at it in context of a problem. So let's go there next. So what that construction leads us to is a strategy for non-homogeneous linear equations. One is to find our n solutions to the corresponding homogeneous version. So that would be the right-hand side equals 0. And we've seen this before. Check. Then we're going to find a single solution, this non-homogeneous part. That'll be new. And then we'll build the general solution out of those two building blocks. Our corresponding solution here from 1, and our new term here from 2, and the general solution is just the sum of those two functions. For most people, this makes a lot more sense seen in context rather than in the abstract, so we're going to go there next.